Hello, I'm Amilendra. I'm a software engineer at ARM. And today I'll be briefly explaining to you two functions that we added to the ARM backend of LLD that will be useful for embedded development. The first is CMSE, which is also abbreviation for Cortex-M Security Extensions. It's also known as Armv8-M Security Extensions, so ARM Trust Zone for Armv8-M. Under CMSE, security is achieved by dividing physical memory into secure and non-secure regions. The secure region also has a part called non-secure callable region that is used to access functionality or resources in the secure region by the non-secure memory. A CMSE application generally has two parts, a secure part and a non-secure part. As the name suggests, the secure core resides in the secure memory region and the non-secure resides in the non-secure memory region. And these two parts are generally developed independent of each other. During the secure core development, the objects in the secure core has functions that are meant to be accessed by the non-secure core. These are called entry functions. And during the linking of the secure core, the linker creates secure gateways for each entry function. And the entry functions reside in secure memory, and the linker puts the secure gateways in the non-secure callable region. The linker also outputs an import library, which is a relocatable file that has a mapping from entry functions to its corresponding secure gateway addresses. And the non-secure developers get this import library from the secure developers and link it with their non-secure objects. And any calls to the entry functions are translated by the linker to go through the secure gateway. And this is the final simplified view of the final CMSE application, where the calls in the non-secure core goes through the secure gateways to the entry functions in the secure region. Big Endian support for ARM. Endianness is a very simple concept, but it's the most complicated simple thing in the world, as a colleague at ARM likes to put it. There are three independent things that could be big or little Endian: L-file metadata, instructions, and data. AArch64 has only one big Endian configuration, and the ARM architecture has more complicated configurations. Early ARM CPUs before Armv6 supported a big Endian configuration called BE32, and all the previously mentioned aspects are big Endian, and it works only for word-aligned accesses, which wasn't a problem for pre-Armv6 CPUs. But then in Armv6, we introduced unaligned accesses, which made BE32 insufficient. So BE8 was introduced as a result. Everything is same as BE32 except for instructions in executables, which are little Endian. So to avoid ABI breaks, the linker took on the responsibility of changing the Endianness of instructions when creating BE8 executables. We needed to break some assumptions in the LLD backend for LLD ARM backend, because it assumed little Endian because it was concentrating more on Linux development. But we went ahead and did it because it would make BE8 support much easier. And after adding BE32 support, we had to make some small adjustments to add BE8 support. And this is still work in progress. So here are some useful references. And any questions, I'm happy to take after the speech. Thank you.